All right, everybody, we are back. We're going to be looking at materials and product and mechanical failures. And our presenters this are Dino Mattei. So Dino is a senior consulting forensic engineer. He has more than 30 years of industry and academic experience. He's been the lead investigator on more than 2,000 forensic investigations. And his specialties include failure analysis, product liability, plumbing systems and component failures, oil spills, corrosion, metallurgical and fractography investigations, insurance fraud investigations, and personal injuries. We also have Eduardo Meri presenting. Eduardo is the fire protection practice lead. He's also a materials forensic engineer. He has more than 20 years of experience performing failure investigations. He's led over 1,500 forensic engineering investigations. He's an expert witness in several judicial proceedings and hearings. His specialties include fire protection systems, mechanical, plumbing, and HVAC systems, product liability, personal injury, fuel oil installations, static equipment and ONG, metallurgy, and materials. So I'm going to pass things off to Dino here. Dino, if you want to go ahead, you can unmute yourself as well. Dino? Oh, there you are. Dino, can you hear me? Dino, did you get? Oh. Dino, did you get the prompt to share your screen? All right, I'm just gonna give Dino a quick call.
Eduardo, do you mind if I do a quick sound check with you?
Yeah, I'm here, ready to go.
Okay, great, thank you.
I can start the first couple slides, which are very general.
Let's, just in case if Dino is like right on the brink of getting on, let's just hold off for like a minute if you don't mind.
Sounds good.
Thank you.
No, we still can't hear you. Sorry, everyone, we're just technical difficulties. Just bear with us 1 minute.
Mark, do you mind if we start with Eduardo and perhaps while you're
Sure. Why don't we do that? Eduardo,
yeah. I'm ready to go. Okay, thank you everyone for joining. I'm gonna show my screen here. Just give me a second. There we go. Can you see my screen, George and Mark?
Yeah, looks good, Dean.
Okay, fantastic. Okay, again, thank you everyone for joining. I'm going to be chatting with you today about some material failure cases or very strange material failure cases. Just to begin, the failure modes in materials can be classified into 5 different ones: fracture, fatigue, wear, corrosion, and creep. And each one has a particular characteristics and the way they present to the trained eyes or examination techniques. And in general, why do failures happen? So there's many different reasons why, but some of the most important ones include service or operation conditions, say harsh environments, running constantly or heavy loads. Improper maintenance is a big one. Obviously, manufacturing deficiencies, some design problems. We also have the well-liked installation deficiencies, wear and tear. In many cases, when the components reach the the expected lifetime, they show wear, tear, and fail because of that. Acts of God, of course. Negligence. Negligence is an important one. It can be linked to many of the other ones, and it in many cases we see claims due to negligence because of misinterpretation of codes and standards or good engineering practices as well. We also have insurance fraud as part of the claims we see and the type of failures we see. Break and entry, and surprisingly, revenge. That comes up in the list as well. I hear someone in the background. Is that Dino or someone else?
Yeah, I just muted Dinu. Sorry for that.
No worries. Okay, so if Dino's ready to go, maybe we can go in order.
Eduardo, I'm just gonna have Dino try and unmute again, and let's just see if it's working now. Dino, can get an audio test?
Yeah, can you hear me now?
Yes,
I think so.
Yes, I can hear you.
Can you hear me?
Yes.
Okay.
Oh, now we got it. Sorry, Dino, I gotta make you presenter now, though. Thank you, Eduardo.
Sure. Just go to the coffee roaster fire slide, Dino, and you can start there.
I'm sharing my screen with you guys. Do you see? Hello, everyone, and welcome to our national tour. And I apologize for the technical difficulties. I'm a materials engineer. I'm not an IT specialist. So once again, please accept my apologies for the problems. In our line of business, we're encountering a large variety of failures. Some are very common and some are not so common. Regardless if they are common or uncommon, there are only 5 different failure modes for materials. They can fail by fracture, by fatigue, by wear, by corrosion, and by creep.
Sorry, Dino, do you want to, I think Eduardo covered this. Do you want to just start with your first case study?
Oh, okay.
Yeah, I think he ran through these for you.
So among the interesting and unusual cases that I encounter in my experience, I want to share a few with you. And first one, it involves a fire which occurred in a coffee roaster. A coffee roaster doesn't look very special from the outside, but it's very important for coffee makers because this is where the coffee is roasted, and it's dark roasted or medium roasted. It depends on the temperature of which the coffee beans are heated. So the coffee beans, the green ones, are put into this machine and they are heated to a certain temperature to reach the desired properties. This coffee roaster was about 20 or 30 years old, and they encountered problems in the past with some of the rivets. Inside the roaster, it's like a tower, and at the base of the tower, there are some steel plates which are perforated and which allow air to go through to adjust for the temperature. These plates are secured to a frame using some rivets, and over time, these rivets were deteriorated and the plates lifted, jammed, and the motor shaft broke. The coffee self-ignited. I did not know until I was involved in this investigation that coffee is actually very hard. So it was the coffee beans that degraded the rivets, allowing the steel plates to lift and to jam. This is a section of the rotor for the roaster, and you can see it was heavily deformed. It shows heat discoloration and some post-fracture damage, showing that it was continuing to rotate after the fire started. The next case, it's also very interesting. It is sad because one person was left with a damaged hand. It involves a pulley machine from a gym. The pulley machine is designed with some carriages which can go up and down along the columns, and you can adjust them at the desired position. Each column is provided with holes where there is a safety pin which can engage, keeping the carriage in place. This is the incident pulley carriage from the incident pulley machine, and you can see above 2 holes and 1 hole below, and the pin engages in one of these holes. There is a warning label on the machine saying that the carriage will have to have the pull fully engaged, and if it's not engaged, the carriage could drop down. This is a reconstruction of the accident, how it happened. So one user was pulling the cables when all of a sudden the pulley carriage dropped onto his palm, causing him a personal injury. As I mentioned earlier, each column is provided with holes where the safety pin will engage, and each hole is numbered. For that particular machine, there were 22 holes, and they were numbered 1 to 22. The user wanted to use position number 6, and you can see number 6, it's stamped on the column. However, it's stamped a little deep. So without realizing, the user set the pin which entered into the round shape of the number 6. So it was not fully engaged, it was only partially engaged, and when he started to use the machine, the pin disengaged from the 6th position and it dropped to the floor on his hand. A very interesting case that we were involved in was associated with a chocolate manufacturer. This is high-end chocolate, and it was successfully sold for years. However, one day the customers started to complain about the fact that the chocolate has a weird taste. So this is, as I mentioned, this is high-end chocolate. All the receipts were verified, all the procedure, all the machines were checked, and the problem continued to persist, and the number of complaints grew and grew. The manufacturer retained us and asked us if we can help determine what caused the chocolate to turn bad. It was an interesting file also because they sent us 30 boxes of chocolate to try. And it was so good that at one point I had to ask my colleagues to stop eating it because I did not have any samples left. We received a box of chocolate from an old batch and a box of chocolate from a newer batch. Interesting enough, and I learned it during this investigation, chocolate is the best absorbent of flavors. For example, if you have a piece of chocolate and you put it side by side to an onion in a fridge and you leave them in the evening, in the morning you will have onion flavored chocolate. Coming back to this investigation, we were told that the boxes were provided by a different manufacturer, and they were provided like an open card box, having on the lid a cellophane window. This cellophane was glued to the underside of the lid, and we examined an incident box and an exemplar box, and we found that in the glue there were traces of solvents. The manufacturer of the box replaced the glue with one which was not food rated. So all the solvents from the glue caused that chocolate contamination. Nobody got hurt. Nobody ended up in the hospital. However, it was loss of reputation, loss of revenue for the chocolate manufacturer. So based on our investigation, he reached to the manufacturer of the box and they resolved the issue. Our analysis was done using a method called FTIR, and in this method, you obtain a spectra. And the blue spectra in the image is for the good chocolate, and the red one is for the contaminated chocolate. Each peak on this graph represents a chemical compound, and some of the compounds identified in the red spectra belongs to the solvents that I mentioned earlier. Another interesting case that we were involved in was associated with significant mold formation in the basement of a home. This was a home built in 1955, and everything inside the home was original. The piping, the furniture, only the appliances were new. The owners were an elderly couple who used to travel overseas every summer for about a month. And during their absence, the house was monitored by their daughter. The daughter was checking for mail, was checking for break-in entries, making sure everything was okay. However, she did not go into the basement because there was no need. And when the incident happened, it was July and it was extremely hot in Toronto. So when they returned from their overseas trip, they were stunned to see the significant amount of mold that formed in the basement. Restoration companies were asked, plumbers were asked to attend. Nobody could determine where the water was coming from, because in order to have the mold, you have to have water and have to have humidity. These are only two images from that house, and you can see the extent of the mold on the ceiling in the basement. We turned the water on, nothing happened, no leaks. Upon examining the pipes, I observed that further away from the shuttle valve, the water line separates into two sections. I don't know if you see the cursor on the screen, and you can see water droplets on the pipe until to this bifurcation. From this point onward, the pipe is dry, and from this point into this direction, the pipe is wet. Under the pipe, there were some glasses which were filled with water that dripped from the pipe. It was very curious that the pipe was dry in one branch and it was wet on the other one. Upon examining further, I went upstairs and I saw this old toilet which was leaking. So the wet branch of the pipe was providing water to the toilet, while the other branch was providing water to other sections of the house. Water that enters into a house usually enters at 4 degrees Celsius, more or less. During that particular month, it was very hot, the AC unit was not on, and when water entered the house at 4 degrees Celsius and it reached the ambient temperature, which was much higher, it started to condense. because downstream from this bifurcation, nobody was using the faucets or the appliances. The water was stagnant and it reached the equilibrium temperature with the ambient. On the other hand, on the other branch, because it was ongoing call for the water was continuously passing through it, not having enough time to reach the ambient temperature, and the significant difference between the temperature of the water that entered in the house and the temperature in the basement caused the condensation. So by replacing the toilet, this problem was solved. Straight current corrosion is a phenomenon which is exactly what the word says, a current which travels in a path that it's not designed for this. In this particular case, I'm going to talk about a home where the entire piping in the basement, including copper pipes and steel pipes, were corroded, as you can see. You can see it also on the top of the hot water tank. The pipes are gone, and you can see the significant corrosion on our gas lines as well. The home was not occupied because the owner was in a retirement home, and somebody was checking the house once in a while, but again, they did not check the basement. So when the owner returned to retrieve some belongings from the home and she entered into the basement, she was shocked to see the extent of this damage. This is a close-up view of one of the copper pipes which was corroded by a straight current corrosion. Our investigation revealed, and it was the plumber who grounded the system in the wrong way, allowing the current to travel through the metal pipes. We looked inside the copper pipes, and other than some patina, the pipes were in very good condition on the inside. So the problem was definitely from the outside. Straight current corrosion can occur in underground pipes as well. If there is an electrical cable or a metal structure close by and the conditions are favorable, then the current flows from one source to another, leading to the pipe corrosion. In this particular instance, we are looking at an 8-inch diameter pipe that was associated with a warehouse. And during one night, the pipe simply exploded, causing the concrete floor to disintegrate and causing further damage throughout the building. You can see that the force of the explosion was so high that it caused concrete to separate. What caused the corrosion in this particular case was the presence of an old railway track in close vicinity. So there was a flow of current between the railway track and this pipe. What is typical for straight current corrosion is the fact that it's very localized and the pipe is not affected inside. You can see on the left image the typical appearance of an underground pipe which is affected by straight corrosion current, and on the right side image you will see the interior of the same pipe which is basically not affected. This is another pipe that corroded due to straight current corrosion, and the features that are associated with this degradation mechanism are more visible here. The scoop-like features on the surface of the pipe are usually typical for straight current corrosion damage. And the last case that I wanted to present to you is the strangest of them all. These images were taken in a building which was used as a film studio. And on the right side image, you can see that the stairs to the basement are not accessible because there is a significant amount of water. Long story short, during winter time, the building experienced some freezing, which allowed water to discharge and fill up the basement. The problem with this building was because it was used as a film studio. At that time, they were shooting a movie about Chernobyl nuclear reactor. And you can see on the right side image, this is actually a reproduction of sections of the Chernobyl reactor. All nice, very realistic. It looked really like an Eastern European plant. Our problem was that a lot of pipes that you see here were prop pipes, and they were designed to leak. So when we turn on the water, it was very, very difficult to determine which was the actual pipe that leaked and which were the prop pipes. We finally managed to find the culprit, and we determined that freezing occurred because one side of the building was not heated. And with this, I will end my presentation here. Thank you again for participating, and if you have any questions, feel free to let me know. Thank you.
Okay, everyone. Thank you, Dino. Let me just find my slide here. There we go. Mark, can you see my slide properly?
Yes, looks good.
Okay, fantastic. Again, thank you everyone for joining today. I'm going to be presenting three very interesting case studies here. First one, we label it Misfire. And it's a building that's protected with a fire protection system that is based on aerosols. So your typical fire protection system is water-based. You can also have chemical protection systems. You could have gas-based protection systems, foams. But in this particular one, they decided to do a retrofit and install aerosol systems. And I'll show them how they look a little later. But one thing to note here is what you see coming out of the building is not smoke, it's the actual aerosol. And it flooded or filled the entire building, damaging or causing damages to basically everything. This is how the aerosol generators look like, or at least some of them. Basically, there's a chemical inside. When it's activated, it generates an aerosol that removes the oxygen and suppresses the fire. And again, because this was a retrofit, these were installed again throughout the building. There was no water-based fire protection system. Sorry, someone's on the line with the unmute or mute option. Okay. On the left here is how it looks, some of the deposits from that aerosol. At the beginning, some of the first responders and investigators thought there was some sort of a fire somewhere and somewhere in this area, but quickly they realized there was no such thing. It was just the deposits from the aerosol products. On the right, one of the areas where the work to retrofit the protection system was installed. This case, some of the activation boxes, just to show you a bit of the system. And in this particular one area, there was no aerosol generator, so it was relatively clean, and not clean, but relatively clean compared to the rest of the building. One thing to note in that particular case is that, and again, this image here is just a general representation of a building with different zones for the alarms and fire protection system. In a typical building, you would have an alarm system that goes throughout the building, throughout the different zones, but particular zones of the building are piped independently. So there's going to be a valve and a piping system to zone 1, zone 2, 3, 4, and so forth. And there are a number of reasons. One in particular is when you have additions. Another one when you have different systems or requirements. Say that you have a drive system requirement in the parking garage, or you have storage in a particular area that requires larger piping. So then you have different zones to accommodate for that. In the case in question, one of the situations that we had to account for was the activation of all zones at the same time, right? And the sequence of events, or the sequence in which the activation occurs in a system like this is you have the detectors, or the smoke detectors, heat detectors, or manual pull stations, and then you get all those signals into the main alarm panel. There will be a visual and audible alarm that indicates to the occupants that something is happening. Then in a system like this, there is the opportunity to abort the activation. So there's an activation delay, there's an abort switch, and then finally, after that time has elapsed, then the signal goes to the activation panels and the aerosol generators go on. And again, this was not supposed to be this was not supposed to activate in all zones at the same time. However, again, part of the investigation is to understand why that happened, and to try to determine who was responsible for that particular issue, either with the installation, with the logics in the panels, with the work that could have been done or being completed at the time. Again, one of the strange claims. A second case study I have for fires. I want to bring up some commercial kitchen fires and fire suppression systems. This is a very standard, nice-looking commercial kitchen, and I don't know how many of you have seen a commercial kitchen after a fire, but I'm going to show you a couple of images here. Yes, this is pretty much how they look like. It can be a bit of a mess, if that's an understatement. On the figure on the left is the kitchen area, and the figure on the right is I'm showing the dining area. And you can see how the fire spreads, the smoke damage goes well beyond the area of origin, and then we have other combustibles that catch fire and create huge levels of damage throughout the building. In commercial kitchens, the main fire suppression system, or the required fire suppression system, is wet chemical agents. And they can activate two ways. One, by a manual pull station, and two, by some fusible links that automatically activate the system in case of a fire. And in this image, I'm showing one of the releasing module on the left, which is tasked with activating the or opening up the wet chemical cylinders that are being showed on the right. And then once those pressurized cylinders are open, then basically just that chemical flows through the nozzles directly onto the appliances. Obviously, any fire that may be present there. It also goes into the hood, the exhaust duct, and normally is able to extinguish the fire or control the fire until the fire department arrives. How that release model look like inside? It's basically, if you see on the figure on the left and on the right, there's two wires coming in, some levers. There's a canister of pressurized nitrogen. The one wire goes to the manual pull station so you can activate the system manually. And the other wire goes to the fusible link. So whenever the system activates because of a fire, it just goes automatically. And then what happens is we have a compressed gas cylinder that is triggered or fired by a triggering pin here. And that pressure will push open the valve in the wet chemical agent cylinder. Similar story on the one on the left versus the right. Main difference is the one on the left connects to the cylinders via some piping and some fittings. The one on the right connects to the tank very much directly, right through just one gasket area on the top of the tank. So having said that, in the case we're working on today, this case I'm presenting to you, the system did not activate and did not stop the fire from spreading. So the question comes to why? And understanding whether the activation or the releasing module is properly activated was critical. In both cases, the modules activated, and in one case, the tank did not open, the valve did not open. In the other one, one of the tanks opened, the other one did not. So again, just this is a schematic of how the system should work. Upon the detection of fire or automatic activation, the chemical agent goes directly under the appliances and the fires and suppresses it. The canister, the compressed gas canister here on the right, is tasked with opening those wet chemical agent cylinders. And interesting enough, the standard requires for inspection of those cartridges. And the standard very generally refers back to the manufacturer instructions. And when you get to the manufacturer instructions, basically there's every 6 months, there should be an inspection, a test of those cartridges. And surprisingly, they're very small, and you can weight the cartridge, and by means of understanding the weight difference to an empty cartridge, you can tell if they're full or not. And in such a small volume, you can pack quite a few grams of compressed nitrogen there. In any case, in both cases, in one of the two cases, we came up with the conclusion of, or the opinion of, the piping or the tubing, the fittings were not properly tightened and leaked. In the other one, we worked with the theory of the seal of the cartridge leaking over time. And remember, these cartridges are pressurized about 2,700 psi. So 2,600 psi. If you compare that to your regular tire in your car at 30 psi, you can see there's a very big pressure in these containers. Moving on to my case study number 2, sump pump down. And sump pumps are a very interesting mechanism or device. And I get a lot of questions from my clients regarding sump pumps. We actually do quite a bit of presentations during the year, and this is one of the favorite topics of some clients. Actually, they are very simple devices, electromechanical devices, but you can find a lot of issues, including, but not limited to, the float switch that I'm presenting here. I have an X-ray picture on the right showing some of the internal components. And there's a number of things that can fail with this. You have the micro switches. You have that can fail because of electrical shorts. They can fail because of water intrusion and corrosion. This float switch itself can fail because it doesn't have enough space to move up and down, or the strap is too long or too short. Again, a number of situations that can happen here. Another interesting one comes to the start capacitor, and basically it's an electrical component inside the unit that allows it to start rotating. And if they're not properly manufactured or installed, they can fail prematurely. Remember, all of this mechanical equipment will fail eventually based on wear and tear. But it's the premature failures that we're looking after in most of these cases after a year, 2, 3 years. One other interesting case involves the impeller or drive shaft that seizes, and that can be because of a number of things including lack of operation or improper manufacturing, jamming because of foreign material. And next, I can tell you about the backup systems and the check valves. So most of these sump pump systems should have a backup system because, again, like I said before, they're bound to fail eventually. So you need to have a backup system to, activate once the main or the primary fails. And then the check valves, like I'm showing here, they can also fail, causing the system to operate continuously or more frequent than normal, and leading to premature failure. Okay, so that was a bit of a understanding or telling about how sump pumps work and fail. This is the case I want to refer to. And interesting enough, it's a relatively new property, new house. The installation of the sump pump and the drainage system was done such that the piping coming out of the house was buried underground, and you can see the installation on the left in the sump pump room. The outside, there is an interesting configuration of that discharge pipe. Basically, this is what it should have looked like. There is the pipe coming out of the sump pump, goes through the wall, and then discharged to the outside, either directly to the outside or through a discharge pipe or a drain pipe that has to have an open air a gap just to prevent any back siphoning, as well as in case of blockages, the water has somewhere to go. So this is what it should have been. This is what it should have looked like. And in yellow here, I'm showing what was actually done, right? So they did not install this open gap here. They went through down into the ground, and then they decided, okay, I don't want to dig that deep anymore. Went up again and back out. And again, all of this situation creates spaces for water to be trapped, freeze over the winter time. And then once there's a blockage, there's nowhere for water to go, just back into the basement. My third case today is one of my favorites. It's labeled cold steel, and you're gonna see why very quickly. So the Titanic. Who doesn't know the Titanic? And it was thought to be unsinkable because it was made of steel and so large that nothing could bring it down. I'm going to show you a couple things about the Titanic and another case that resonate. So the Titanic, how it looks, or representation of how it looks at the bottom of the ocean, the experts investigating found significant cracks throughout the hull, and different locations. And one of the things they compared to was some of the Liberty ships that cracked. And again, Titanic is 1919. Liberty ships are post-war, so or pre-war, just 1940s, 50s. And we have very similar failure modes here, right? The very simple, very elemental test that is done on most steels to understand how they behave, how or what's their ductile or brittle behavior, and how they behave under temperature, is something that probably wasn't properly done or done at all in both of these cases. And the specific case I want to talk to you about is a login forwarder, which was operating in the Canadian North during the winter time, and it failed catastrophically, following breaking off the buggy on the back from the tractor on the front. There's a chassis that connects the two, and that chassis broke off, and the equipment just toppled over, and obviously causing significant damages to the equipment, personnel. This is how some of it looks like. You can see on the left the tractor, on the right the buggy, and then there's that chassis that connects. You can see part of the chassis here that connects the buggy to the tractor. Surprisingly, jagged fracture. You can see the fracture on the chassis here. You can see the fracture on the chassis here. The temperature at the time of the loss was around -30 Celsius, and that's going to come into consideration later on during the investigation. But the first thing that comes to mind when looking at this fracture is how brittle it looks, how far the cracks propagate from the point of origin, and how jagged they are. Look at the cracks here throughout this area where the bolt was located, and this is reinforced. These are reinforced areas that should have probably bent and deformed, but it's hard to see. It's hard to find failures like this today, because normally the failures would look ductile and not brittle like this. This is at the back of the buggy where the chassis connects to the buggy. You can see even though there's no fracture in this area per se, no separation of the chassis in this area, it looks like the forces were such that cracks propagated from the corners, which obviously act as stress concentrators. This is the other side. We also have a similar pattern of cracks propagating from the corners here. And how the fractures look under the microscope is very interesting. It's fascinating, actually. And on the left, you can see the fracture morphology of a brittle fracture. And on the right, it's the one of a ductile fracture. The main difference is in say when we're talking about a material that's supposed to behave ductile and absorb a lot of energy, say during impact or bending or flexural, but instead of failing ductile, fails brittle, and that is because it was operating under temperatures below its ductile to brittle transition temperature. Then we get that fracture, that failure that is, first of all, instantaneous. It propagates much farther than it should. The cracks just grow very large, and it's just like a piece of glass when it fractures, very brittle, as opposed to say a paperclip that we can bend many times before it fractures. If we do the same with a piece of a thin glass, it's just going to shatter right away. And these are some of the curves that I was referring to, the DBTT transition curves. And on the left here, this is just a schematic of how they look like. Basically, some of the low carbon steels have a transition temperature, around minus 50 Celsius. And basically, as the temperature drops, we get a less energy being absorbed during the test. And then at some point, the energy just drops significantly, transitioning to a brittle type of fracture. And we can determine what is the transition temperature for that particular steel. In a case like here on the right, which is the A36 steel, which is a very common steel used for construction of tanks and other equipment, we have a transition temperature that is roughly around 10 Celsius or so. And that what that says is we can't use steels like these on equipment that is subject to flexural loads or extreme flexural loads or impact or other applications where the material should have a transition temperature much lower. And in this case, that's pretty much what could have happened. The transition temperature of the steel used was not sufficiently low to remain ductile during the operations in the Canadian winter, and it failed catastrophically in a brittle manner. For now, that's about it for me. If you have any questions, I'll be happy to take them, and I'm sure Dino as well.
All right, thank you, Dino and Eduardo. Dino, do you want to unmute, because we've got a couple questions here. I will start with one for Eduardo, since we just wrapped that case study. So was there a manufacturing defect with the steel, or was it an improper material choice given the equipment and environment?
Well, in many cases, we don't get to see the full extent of the results, and this was probably one of those. But I can tell you from similar cases involving brittle fractures on equipment that it's in most cases it's a poor choice of material.
Okay. Dino, are you there? Okay, Eduardo, I've got another one for you here. So this is the fire protection system. Do you know if there are any fines associated with the release of aerosol pollutants into the atmosphere? That's a very specific question.
These aerosol systems are non-toxic. I'm not aware of fines with the release of these systems. Basically, remember that any and all fire protection systems are actually fire and life protection systems. So they are designed and intended to protect property, but most important, life. So it's the fact that some of these, say, foams or gases or aerosols are released. It's the intent is for to save lives, and I doubt there would be some fines associated with that.
Okay, Dino, any luck with the audio? All right, well, Eduardo, you can answer this one.
Yes, sure.
Could you explain creep in a little more detail?
Yes, of course. So creep is a mechanism under which a material will experience some. Imagine you have a ruler, say a 12-inch ruler, and then you apply a load on each side on tension. And then that ruler over time is going to elongate. It's going to become longer and longer. Now, if it's a very elastic material, say like rubber, it will simply elongate for a long distance without major damage to it. If it's a material that suffers from crack initiation and damages inside due to dislocations like most metals do, then as that creep goes on, then there's some cracks that develop inside, particularly at geometrical areas where there's some notches or some changes in thickness or small curvature angles, and then, or defects, internal defects or external defects, and then the crack's going to grow from there and obviously create a fracture, a failure. Creep is not only happening in metals, it also happens in plastics. Some polymers are susceptible to creep, and a very famous case is that of the toilet connectors, the plastic toilet connectors, the white ones that were, still in service, many millions of them, I imagine, and that material is susceptible to creep and will just develop a crack and fail over time.
Okay, so another question to do with the suppression system. Would the regular inspection of the commercial fire suppression system identify the problem with the nitrogen cartridge in your example?
Yes. So let's remember. So well, let me rephrase that. It depends, and that's a favorite for my colleagues. So it depends. There is a time interval for the inspections. In this particular case, it's 6 months. So say that the cartridge is damaged and it's leaking, and after the 6 months period, the inspector comes in and tests the cartridge or weighs the cartridge and determines that the weight is either empty or half full. Then you can pick it up. But if the leakage rate is faster than that, then say after 2 months the cartridge is empty, then obviously you have a 4-month period of time in which you have no protection for that system. Again, I just want to make clear that this is an unusual case. It's a strange case. It's not something very common. Typically, they're very robust systems, and we don't experience those sorts of things. But again, that's why we're talking today about strange claims, right? Just the unusual ones.
Could you just go back and so what ended up happening with the sump pump case study? So what brought you to the file?
Well, in most sump pump cases, there's obviously the flood, and damages can be, as small as $5,000 or as big. I've seen as $300,000 with sump pump issues, not only for the property damage, but hosting the insured somewhere else while repairs happen. The main issue with sump pumps, I would say, is that there's no, or the actions are delayed, or the repairs occur before proper documentation is done on the system. And in many cases, the pumps are blamed for the problem. The pumps are removed and sometimes sent for examination. But the pump itself is not the only part of that puzzle, and it's important to understand the installation, other considerations in the area, but also remember that a pump that's been in service for a number of years is prone to failure just due to wear and tear. So again, understanding all of those factors provide for a better a better case for you and better outcome if there's possible subrogation.
Okay, thank you so much. Thank you, Dinu. Thank you, Eduardo. That was fantastic. Everybody, we're actually taking a lunch break now. So it's 30 minutes, and then we are going to be back. We've got two extremely interesting mechanical cases with Michelle Bradley and Andrew Graham and Tata Hulan from Harrison Pensa. So that will commence at 1:10. So we'll see you then. Thank you very much. Thank you again, Dinu. Thank you, Eduardo.
Thank you. Bye.